All right, so I'm Chris Blythe, and today I'll be talking about exploiting convolutional filter patterns for transfer learning. So first question is, what is transfer learning? Transfer learning is transferring previously learned knowledge to new conditions. So what do we mean by this? Well, given a source domain of samples with a certain distribution, we can train a model to fulfill a task. From that model, we can extract knowledge in the form of general or common representations. We can retrain or fine-tune a target model with this common knowledge and use that common representation to improve or get a head start on training, even though the target task and domain may differ. So why is transfer learning important? Well, deep network training requires lots of time and data. Labeled data is very expensive, and while we may have the data in source domain, we may not have enough information in the target domain. Also, models performing tasks that differ from their original training will underperform or may underperform, requiring expensive retraining and fine-tuning. So essentially what we can do is reuse what we have already learned. But to get right into it, this is the standard loss for a CNN. We're all familiar with it. So given an input image X, we can volve over it using weights W arranged in filters, and this forms our network Z, which outputs a prediction. The prediction is compared to the target label Y, which is our ground truth, which informs our loss. During backpropagation, we use the derivative of the loss to update our weights. And throughout the depth of the network, these weights can form different filter patterns and shapes. So the questions become, the authors asked three separate questions about these different filter forms. Are filters separable into clusters? How similar are filters inside a cluster? And how filters are distributed over all these clusters? So just to review on distribution, when it comes to distribution over a cluster of filters, we can use the multivariate Gaussian distribution, which can be calculated for all the weights in a cluster, using the mean of all the weights, and the covariance, which is the correlations between weights in a cluster. We can create a total distribution by taking a weighted sum of each individual cluster distribution, giving us a Gaussian mixture model of the weights over all of the clusters. So the authors of this paper attempted to use this knowledge by applying CNN filters to known good networks, first using AlexNet. And they took 3x3 filters separated into 10 clusters using the k-means algorithm. So what that looks like is here. This is the visualized covariance by cluster. So each one of these is the covariance for each cluster. It gives us a 9-dimensional matrix for covariance. Yes. And then they visualize the mean as well, which in this case, yes. Okay. So we visualized the covariance by cluster. Now we visualize the mean by cluster, and this is a 3x3 filter. So all the filters for this cluster put together into one stack to show the mean of that cluster. Yes. So they did that. They performed this experiment on AlexNet first with the ImageNet dataset, and then with the Places dataset. So this is the covariance for AlexNet on Places, and this is the mean for AlexNet on Places. And then they did the same thing, but this time for a different network, VGG16. First on the ImageNet dataset, again, this is the covariance for each cluster, 9x9 matrix. And then they got the mean for the cluster of filters on ImageNet, again on Places, and then the mean on Places. So the authors then analyzed the resulting distributions of the filters over all the clusters. First, AlexNet on ImageNet, and then on Places. So the distribution here is similar. And then on VGG16, the x-axis here is the filters by cluster. So each one of these is a cluster, and then this is the number of filters that went inside of that cluster. Yep. So so then they did this on VGG16 on ImageNet, and place distributions. And what we've seen is that the distributions are similar within the network. As you can see here, the distributions are similar within the networks, but they differ between the different models. So same models have a similar pattern within their distribution regardless of the data. So given what this experiment has shown, the authors had a goal. The goal was to transfer the relational statistics of the filters with the hope that this will produce better representations quickly. They tackled this problem by asking what makes a good filter, and kind of just answered that question. Well, we can take proven filter pattern distributions taken from known analyzed models that work the way we expect them to. So this method attempts to take advantage of these statistical patterns in known well-trained networks by capturing those statistical relationships using Gaussian mixture models, which we explained earlier. So given a new network, we can transfer these filter relationships through a regularization term R, and R encourages the new network to learn similar weight distributions as the well-trained network. And then we can back propagate the loss through the added regularization derivative in respect to our weights. So what does this regularization R look like? Well, it's essentially the negative log likelihood of our distribution over the weights in a layer. And negative log likelihood gives us the estimated parameters required to produce the distribution that we are looking for, P, allowing R to encourage the loss to produce the same distribution. So total regularization for all the weights is equal to the multivariate Gaussian per cluster, which forms a Gaussian mixture model for all the clusters in K. Then we take the log likelihood to estimate those parameters, and then we do that for all the filters. So backpropagation of our regularized loss needs a derivative form. Derivative of negative log likelihood is expensive, so we approximate derivatives by using mixture components the mixture component that contributes the most. So the derivative results in, we essentially select one distribution and take the derivative of that, which gives us the weights minus the mean of our chosen distribution times the inverse of that same distribution's covariance matrix. Mm-hmm. Yes, it's an optimization because it has the max contribution anyway, so we pick that one. So for our completed loss term, we have our standard loss, our weight decay, and then we have a regularization term with a lambda, which is a hyperparameter that controls the impact of that regularization. So they then tried different experiments. First thing they did was they tested for feature generalization by training one network using regularization and one network without. They did this on the CFAR10 data set, and what they did was they trained the network and froze it at multiple epochs and let the training and testing continue. So they did this. So they did this for 10,000, 15,000, 20,000, and 25,000 epochs. These results are for the 10,000 learning iterations, and they show the difference between test and training loss. In their words, meaning how general are the features that are created. This proves that they're general because the slope of this change signifies how quickly the test loss deviates from training after the network was already frozen. In this example, the slope is very steep, which signifies specific features were learned. And as you can see, regularization provides a smoother slope, which means more general features were learned. And so they trained the network up to a certain point with regularization and without. And then they just took the classification layer and kept training that top layer, right? And then as time went on, as those iterations continued with the training, there was a deviation from the test and the validation because those features were specific, right? It was too early in training to be doing that. So part of that is, as you can see here, they went on to train more feature or more iterations, 15,000, 20,000, and 25,000. And as you can see, the non-regularization curve does get smoother as well with the more training, because by that point it has learned to be more general, it has done dropout or different things in order to achieve that. Because you're not training the entire network, you're just training this top layer, and it's using these underlying features with it, which have been under-trained. They're underfitting.
Yeah. So it's nothing to do. Yeah. Okay.
All right, so as we can see, the regularization performing better is consistent through all the different stop marks, different iteration stop marks. So then, so another experiment they attempted was task transference, in which they trained the VGGF network on ImageNet, and then they fine-tuned it on the Places 2 data set. And this shows results of the network with regularization and without regularization. So as you can see here, in blue this time, at 10,000 iterations with regularization, they got less of a loss than without regularization, which means less training but equal performance. And over time, with more training, stopping at higher iterations, we can see that the regularization and non-regularization curves kind of meet, meaning more training is equal performance. But with this method, we get limited training and a time advantage. It's able to do it faster because of the regularization term that they are now using. With enough iterations, they meet up, because there's a certain threshold by which the regularization doesn't really help anymore. And by that point, you've trained the non-regularized network enough so that they meet. You can do it in fewer iterations and get acceptable results. So in the first one with 10,000, it's not as accurate. But if you see the difference between this blue line and this blue line here, between 25 and 50,000, they're very similar, right? You get about similar results with half the number of iterations.
So these first two graphs should be similar until up to 10,000 iterations, but they are significantly different.
They should be similar up to 10,000 iterations. What do you mean?
And they increase at 10,000 iterations, the first graph, increase the second graph at 25,000.
Yeah, but those iterations were done before this graph even started, right? But okay, no problem. Okay, so again, this transference allows for less time training. So another experiment they did was Cross-Modal, and they used this Cross-Modal data set called CM Places, where one scene is described in different modes. Bedroom scenes are defined by real images, clip art, and sketches. So these are different modes of the same scene, bedroom. And this is another example of that. This is a kindergarten classroom with different modes of real image, clip art, and sketches. So the issue that comes up here is maintaining modal alignment to that label, bedroom or kindergarten classroom. So their experiment with this data set was to train a VGGF model on Places data set And then they fine-tuned one model on the clip art data of CM Places data set, another model on the sketch data of CM Places data set. And they compared the results against a converged ImageNet model as a baseline. And as you can see here, this is 25,000 iterations or epochs without regularization, and that got a score of 60.45 in the top 5% accuracy. And then 25,000 with regularization got a marginally better score. The same thing goes with 55,000 iterations without regularization, 50,000 iterations with regularization, again, marginally better score. So in this example, we can see that regularization consistently performs better with less training, giving us acceptable results compared to ImageNet. And they did this. They don't mention it. They don't say how long it took to train the converged ImageNet. They did the same thing again with the sketch data and got similar results comparable to the converged ImageNet. So yeah, in the sketch data, it was not as good as the clip art data, and they do mention this in the paper. They don't explain why that difference exists. So in conclusion, we have shown statistical patterns in known networks. We have captured those patterns with GMM and enforced them with the regularization term in order to get better representations in less time, giving us generalized features that are task transferable and possibly cross-mode transferable.